Okay, so next we'll have a look at the central limit theorem. Central limit theorem is based on the concept that we have already seen, that is the sum, a PDF of sum of the random variables. So it's based on the concept of PDF of sum of a random variable. Now, what is central limit theorem? It states that the probability density function PDF of sum of n independent random variables tend to approach Gaussian density as the number n increases. I'll just write down the statement. It states that the PDF of sum of n independent random variable tends to approach Gaussian distribution as the number n increases. That is the concept behind central limit theorem, that let's say we have n number of independent random variables, and if we add these n independent random variables, the PDF of the resultant random variable will always tend towards Gaussian distribution. Just for an example, let's say we have two random variables whose distributions are given, fx1 spreading from minus x1 to x1. Second one is x2 random variable given by this distribution, so minus 2x1 to 2x2. Now let's say z is another random variable which is sum of these two random variables, x1 plus x2. So if we sum these x1 and x2 and find out the PDF of the resultant, it will tend towards Gaussian distribution, and the range, we know it spreads from the sum of their extreme points, that is minus x1 plus minus 2x1, so minus 3x1, and the other extreme point would be 3x1. So as this number n, the number of independent random, these two are independent random variables, we add these two and we say that the resultant random variable, its PDF will approach towards Gaussian distribution, right? And as this number n increases, in this case we have taken only two random variables, two independent random variables. As this number n increases, it becomes more close to the Gaussian distribution. The resultant, the sum or the resultant becomes more close towards the Gaussian distribution. This is the concept of central limit theorem. Next we have is the concept of random processes. We can simply define random processes as it is the time domain representation of random variable. Time domain representation of a random variable. Okay, random process is nothing but the time domain representation of the random variable, or it is a random variable which is a function of time. You can also say that it is a random variable which is function of time. Alright, so a basic concern in the statistical analysis of communication system is characterization of random signal. That is one of the most basic concern, such as voice signals, television signals, electrical noise, etc. These random signals, all these random signals are the function of time. Therefore, in describing the random signals, we find that each sample point in a sample space is a function of time. I'll repeat this the concept once again. Whenever we go for statistical analysis of any communication system, the characterization of random signals like random noise is a big challenge. Okay, because these random signals are function of time. Therefore, in describing random signals, we find that each sample point in our sample space is a function of time. Okay, we know that for a random variable we have a sample space which consists of different possible outcomes. Okay, let's say this is the sample space and these are the individual sample points or the possible values, right? So each sample point can be represented as a function of time if you are characterizing a random signal. So this x1t, there is another function of time, this x2t, and so on. Okay, for example, very simple example, temperature, let's say temperature of a room for several days. Okay, if we take the temperature of the room for several days, we can easily plot it as function of time. If we take 10 rooms and we measure their temperatures at for a number of days, we can find out these time domain representation of different sample points. Okay, so to determine the statistics of a noise or a random signal, we might take repeated measurements of the output of a signal noise source, or we might make simultaneous measurements of output of very large collection of statistically identical noise sources. And such large collection of these time domain representation of sample points is known as ensemble. We call this collectively as ensemble. Each sample point which constitute random variable can be represented as a function of time if we take the repeated measurement over a time interval or for several days. So that collectively is known as ensemble. Okay, so clearly we can state the difference between the random variable and the random process. In case of random variable, the outcome of each trial of the experiment is a number, is a numerical number, and we can easily see that in case of random process, the outcome of the experiment or the outcome of each trial is a waveform. It's not a number, it's a waveform. In case of random variable it was a number, but in case of random process it's a waveform with respect to time. Now based on this concept of ensemble, we can define the averages in two categories, that is ensemble average and the time average. And time average. So in case of ensemble average, it is represented as expectation of n square t1. Okay, let's say it is one of the waveform, or rather n bar square t1. And ensemble average refers to the overall average of the combined for all the waveforms, while the time average is determined by the measurement on a single sample function at successive times, represented by this. So this is for a single waveform or a single sample point over different time intervals, and ensemble is collectively for all the waveforms. Okay, in general, time average and ensemble average are different. We can say that in general, time average and ensemble average are different, which is quite obvious, right? Because if the statistical characteristic of the sample functions in the ensemble were changing with time, such a variation could not be reflected in the measurement made at the fixed time, and the ensemble average would be different at a different time. is the simple reason behind it. Then comes the concept of stationarity. Stationarity of a random process. So when the statistical characteristics of the sample function does not change with time. Statistical characteristic means the averages, right? If the statistical characteristics does not change with time, the random process, that random process is described as the stationary random process. The random process is stationary when the statistical characteristics does not change with time. Then we have ergodic random process. Ergodic. When the random process is such that the ensemble average and the time average are identical, such random processes are known as ergodic random process. Ensemble average is equal to time average. Such processes are known as ergodic processes. Ergodic random processes. So we can predict that, we can conclude that an ergodic random process is stationary in nature, but obviously the stationary random process is not necessarily ergodic. An ergodic random process is stationary, but the vice versa is not always true. Now let us have a look at some of the statistical characteristics of random process. First is mean of random process. It is represented by x hat t is equal to integral x fx t dx. It is quite similar to the random mean of a random variable, but instead here we are using the time domain representations everywhere. Next we have the autocorrelation function and the power spectral density of a random process. Autocorrelation function and power spectral density. The autocorrelation function is represented by Rx tau, and this is your autocorrelation function of a random process, and it is mathematically equal to expectation of x t plus tau into xt. It gives the correlation of the random process with the time shifted version of itself. You can clearly see from here, it is the expectation of this is the time shifted version of the random process, and this is the random process. It gives the correlation or the similarity of the random process with the time shifted version of itself. Okay, so this is your autocorrelation function. So if we look at autocorrelation function at tau is equal to 0, it is expectation of x square t, which is nothing but the mean square value. So we can say that the mean square value of the process, random process, can be obtained from the autocorrelation function at tau is equal to 0. Mean square value or the average power of the random process can be obtained from autocorrelation function at tau equal to 0. Next, we know that this autocorrelation function Rx tau is an even function of tau. Rx tau is equal to Rx of minus tau. And another property of autocorrelation function is that Rx tau, the autocorrelation function, has its maximum magnitude at tau equal to 0. That means this modulus of always less than equal to Rx of 0. Maximum value of autocorrelation function is at tau is equal to 0. Now a very important relationship between autocorrelation function and the power spectral density, PSD. This relationship is also known as Wiener-Khinchin theorem. And it states that the power spectral density is nothing but Fourier transform of autocorrelation function. Or we can say that if you take the Fourier transform of autocorrelation function, it results into power spectral density. It's a very, very important relationship. Next we have is classification of random process. As stationary random process that we have already discussed in brief. We know that the stationary random process is a random process whose statistical characteristics does not change with time. It's a random process whose statistical characteristics does not change with time. This is a stationary random process. So we can say that the shift in the origin is impossible to detect because it does not change with time. Alright. So one of the important mathematical conclusion we can get from here is that autocorrelation function of a stationary random process must depend upon the time difference, that is Rx T1 T2 will be equal to Rx T2 minus T1. It's a very important conclusion that autocorrelation function depends of a stationary random process depends only on the time difference. The next type of random process we have is wide sense stationary random process. Wide sense, or we also call it as weakly stationary random process. It is not stationary in the strict sense because it has only mean and autocorrelation function that are independent of shift of time origin. In case of this stationary random process, all the statistical characteristics does not change with time. So the shift in origin is impossible to detect. While in case of wide sense stationary random process, we say that only mean and autocorrelation function are independent of shift of time. Okay, all the other statistical characteristics, they depend on time. So it's a process that is not stationary in the strict sense and may have mean and autocorrelation function that are independent of shift of time origin. So only the mean, that is xt, is constant. This is one quality, the one parameter, that is the mean of this random process, wide sense stationary random process, is constant, and the autocorrelation function, it depends on the time difference. So these two have to be fulfilled in order to declare a random process as wide sense stationary random process. So this completes your unit number 1 of the CIF. and also the syllabus of your midterm examination. We have covered unit 1 and unit 2 as per the CIF, and yeah, that is all for this lecture. Please do practice the numerical problems from the BP Lathi book and the other sources, whatever you find. Okay, all the best. Thank you.